Hey, fellow biophysicists. So today I'm excited to be talking with Dr. Marco Mauri. He's a researcher currently at the University of Edinburgh. And today we're just going to kind of introduce the show a little bit and discuss, what we mean by biophysics and specifically kind of this intersection of theoretical and experimental biophysics. So Marco, it's a pleasure to have you on.
Hi, Clark. It's my pleasure, actually. Thank you.
So let's just, kind of jump right into it. So when we talk about biophysics, what is biophysics and why do we even think it's useful?
Well, I think there are actually many different ways to define biophysics. Probably I can just give my personal idea on the topic. And for me, it's just the using physical meanings and physical laws to describe biology. It's actually a long trip since people started thinking about merging biology and physics or trying to use them together. We can see directly in the beginning of the last century that people started to describe biophysical problems with the law of physics and mathematics specifically. In my personal idea is also to use quantitative methods to describe biology. So model, computer simulations, and so on. But there are many different ways to describe biophysics, actually. Some of them are actually also more targeted to the quantitative fields, so measuring than describing by itself.
Yeah, I mean, it's an interesting intersection, right? Because on one hand, you have kind of the stochasticity and randomness of biology. And on the other hand, when you think of physics, you think of very deterministic equations and, with a couple simple assumptions, we're able to predict and make predictions about a large class of things. Whereas in biology, things, are going in and out all the time. So it is fascinating to think of, applying this physical rigor to kind of these chaotic biology systems.
Yeah, absolutely. And most of the time, it's also biology that gives new insight in physics. So there are several problems that are not really studied in physics, and biology gives some ideas, and we can actually find new physics behind it. So it's quite
that's
nice merge
interesting.
and exchange.
One kind of informs the other.
Yeah, true. I mean, someone said that you have not to think what physics can do to biology, but thinks what biology can give back to physics. And I think it's actually the right way to tackle this kind of problem and find also new ideas inside biology.
I like that. It's kind of a chicken and egg problem, right? You don't know which one came first.
Yeah, indeed, exactly. I mean, we can say that they had different paths over the past decades, but now we are kind of finding a unified vision. And there are also a lot of exchange between biologists and physicists. For both, I can say that not every time they can speak easily.
Yeah, I mean, there's probably a number of fistfights that have broken out, biologists saying one thing and physicists saying another. But
yeah, true. That's right. And also mathematicians sometimes think that they are speaking differently, but we are all speaking the same language, the natural language. We have just to adjust it in the proper way.
Yeah, you gotta speak to your audience, right?
Exactly.
So I guess kind of additionally, there's kind of even a divide even among biophysics where we have theoretical biophysicists and experimental biophysicists. So, kind of in this show, we're hoping to get more into kind of the theoretical aspect of it. So how exactly do you distinguish between the experimental and the more quantitative theoretical side of it?
Oh, well, actually, I can tell you my experience. So the two are really going together, but if you would like to give a definition of the difference between the two, probably the experimental one is the one that goes in the lab, do something on the sample and measure quantities.
They do the real hard work.
Exactly. While the theoretical one, you sit on a computer and paper and you try to find out the model. So let's say that in one case is the description of the biological part or the biophysical part. In the other case, it's actually the measurement, the quantitative measurements of the events. So that's the difference between the two. But finally, you have to merge together again these two, because you need a parameter for fuel in your model. So you need the measurement, the biophysical experimental part. And to understand it, you need the theory, so the modeling or the simulation part. So in the end, you have to try to understand both and try to use both together.
Yeah, I mean, in a theoretical model, you can cook up whatever you want. You just don't know if it's going to match what you can actually observe. And I guess for experimental stuff, you can go in and observe whatever you want, but you have no clue what the mechanism behind any of it is.
True, yes, it is. I mean, that's modern science. We try to rely on experiments and try to have a theory and after verify it.
Yeah, it's a feedback loop, right? You know, just like how we were saying earlier, biology informs physics, physics informs biology. It's the same thing with experiment and theory.
Yeah.
There's also probably a number of fistfights that have broken out between experimentalists and theorists over over the decades, but so I guess, you know, this is kind of a more loose question, but, you know, what kind of excites you about biophysics? You know, what do you hear about and you're like, wow, I wasn't expecting that, you know?
Well, I can, again, I can tell my experience. So I come from quantum chromodynamics, so completely different field. And after I switched to biophysics during my PhD, what excites me more in biophysics is that you can describe really complex organism events, because I mean, in biophysics, you can fit whatever from ecology down to single bacteria. We have a simple law of physics. So making a sense of what you observe and see. Independently, if this one is a bacterium or a molecule or an ecological problem, but the law that you use, laws that you're actually using are always something that are coming from physics and make sense of what you see. So that's the interesting part. Personally, obviously, I'm working on bacteria, and in my case, I'm highly excited by whatever describes the inner part of bacterium. So composition, allocation of resources. In my case, it's something that I put central to my research, and so on. So all these parts are quite nice. But now people are moving from bacterium to higher scales. So there are researches, we know enough to get to tackle also communities of bacteria and also complex communities, so assembly, stability of communities, and people are starting to work on them. And I think that's the what we are going to do in the near future also with the physics. We're moving from a description of movements of single molecules inside the bacterium up to description of communities. And that's,
yeah, you're trying to really capture like a more multi-body effect. Bacteria don't happen just as a single little guy floating around. And it's interesting, kind of this you know, length scales that we talk about in physics. So, you know, we do have in biophysics, we do, you know, you think of just biology, you're like, oh, that's about this, but there is kind of this huge dearth of length scales that we can probe at. And so each range of biophysics looks at a different thing, whether you're looking at, you know, a single organism or multicellular organism. There's a lot of interesting kind of things that you can dive deep down into and get in the weeds about.
Yeah, that's true. So the problem of different scales is something that it's always present in physics from ancient time, and also in the last century we had this problem of trying to figure out how to switch from scale to scale, and we are experiencing exactly the same in biology. So we had the problem, for example, in physics from the description of my case, I can tell you quantum chromodynamics or small particles, how to renormalize calculation from one scale to the other one. And in biology, we're experiencing the same problem. So how to switch from the description of a single bacteria up to a bigger scale. And problems are exactly the same as we thought in physics. So probably we can use the same kind of theories to try to organize better the vision of biology.
Yeah, I mean, isn't that kind of the hope of theory, is to get something that's universal that you can apply to anything, to kind of get an intuition about what's going on?
Yeah, that would be a great step. But we have to go slow and work a lot. So yeah.
Yeah, you always just take you start with the lowest hanging, the easiest problems, and then kind of work your way up from there.
True.
So I guess kind of, this is the introductory episode, so I'm going to kind of make this one a little bit shorter. So kind of my last big question for you then is, where do you kind of see the future of biophysics going?
Wow, that's a tough question. I mean, I told you, I think that biophysics has several scales to describe. For sure, we need better precise measurements. So up to now, we relied on measurements based on chemistry and on, let's say, the biology of the 70s, when people started to really measure stuff and did it precisely. Now we are really moving this paradigm from the biologist, the chemistry, the physicist. So a different kind of way of measuring stuff, just because we need different parameters from chemistry and biology. And I'm not saying that it's better or worse. So better would be for sure, we need measurements. We need a lot of them. And so we need also biophysicists that works with experiments and try to understand something of the modeling part. And regarding instead the theoretical part, I think that we are really moving from the single bacteria up to a bigger scale, like communities, assembly of communities, how communities are established and live in the natural environment. That's something that is actually still unresolved. It's not really clear, this kind of diversity that we have in natural environments. We cannot reproduce it in the lab. So that's a big issue. And on the other side, also the pandemic show clearly that we need something applied to the human. So probably understanding better viruses, how they spread, bacteria they work in the body, and tackling this big problem of antimicrobial resistance. So there are bugs that are now unkillable in the body. Basically, they still they can keep.
Yeah, we keep increasing the quote unquote poison we put in, and the biology finds a new way to adapt to get around it.
Yeah, they're resistant. So we need to understand why this happened and how we can overcome this one. So basically, the three directions that I think are better measurements, precise measurements, modeling regarding how we can have diversity in nature, and stability also in nature. It's also important because we are seeing that the climate is changing, and how will this one impact the form of life? It's important, so stability. And finally, apply to the human.
Yeah, I mean, so I guess kind of recapping that again, it kind of sounds like, we can't have too many theoretical biophysicists because we need measurements. The theoretical predictions we need to make need to encompass all these things. And lastly, we need to be making predictions about things that are very relevant to us human beings. So
yeah, exactly.
That's always the hard part with being a theoretician, right? Is people are like, oh, well, why are you studying this? And you're like, oh, well, it takes a long way to get down the chain to why it's important to the layman on the street. But
yeah, first of all, we have to understand it. I mean, I need to understand, for example, why my research is important, and after I'm able to explain it. Also,
it definitely helps on those late nights when you're like, oh, why am I doing this again?
Yeah, it's true.
Okay. Well, yeah, thanks for being on the show. And hopefully we'll be getting some more of these out. The kind of general format we're going to be trying for is hopefully, the researchers that are coming out with these papers, they're coming out all the time with this great research. And kind of the aim of this show is we're going to be diving deeper into these papers and getting the authors really a chance to bring their kind of words to life, so to speak.
Yeah, thank you for the invitation.
Yeah, thanks so much for coming on, Marco.